Hello guys, welcome back to Maison African Motives. Still working on our revisions for industrial electronics info. In this case, we shall be working on the op-amps, that is our operational amplifiers. Okay, we've got a lot, not that much that we need to consider, just our basic approach so that we can be able to understand our questions, how are we supposed to answer typical questions on our operational amplifiers. So this is just our course layout whereby you need to know the properties, the characteristics, advantages of these operational amplifiers that we are talking about, also to provide the layout of an operational amplifier, to calculate the gain, and also to draw the circuit diagram with the associated input and output waveforms for an operational amplifier that is used as, so we are going to talk about an inverting amplifier, the non-inverting, an adder, which is the summing amplifier. Then we've got a differentiator. We also have an integrator and a comparator. So you're supposed to know the diagram of each because you might be given questions where you need to draw. So you're supposed to know each and every of part of your amplifier part. All right. So the operational amplifier, which is referred to as an op-amp, is simply or at most commonly known is one of the basic building blocks of or workhorses of analog electronic circuits, and is a device that has all the properties required for nearly ideal DC amplification. Remember, amplification is just change of voltages from one to another. So the op-amp is a high gain amplifier and has the capability of amplifying signals in the 0 hertz, that is the DC, to megahertz range. So we are going to talk about from the 0 hertz up to megahertz range that you're given. It makes use of negative feedback to control its functions and can therefore be used to perform many mathematical calculations, this part. And also what is important is for you to know the advantages. Yes, there are so many things that you need to consider, but you need to know your main advantages of op-amps. They might ask you this part of the advantages, that is, they are small in size, they are cheap, they also offer low power consumption, highly stable, and also they are highly reliable. So this is one, these are some of the other things that you're supposed to consider on the advantages. And the characteristics, definitely, yes, you're supposed to know this between an ideal and a real op-amp. So here, there are some of the major things that you're given, guys. As you can see, a lot in terms of infinite gain, in terms of the input impedance, the zero output impedance. So I just want you to go through these, understand each and every part that you are given in terms of the properties that are given between the major one, which is the real, and the ideal op-amp. All right, so they can ask for you to just give a comparison of one or two of those ones that you're given. So what the characteristics mean, so talking about just in short of what you saw on that table, we can be talking about having an infinity input impedance. That is the input impedance, it's infinity, that is endless. We are talking about endless values, means that the op-amp consumes no power at that condition. If our Z-in is infinite, there's no power to be consumed. For zero output impedance, if the output is at 0, it means the op-amp can be connected to any load. That is what it means. But for the infinite voltage gain, if our voltage gain is infinite, it means there is a very small change in the input signal and should produce a very large change in the output signal. Then we talk about the infinite bandwidth, whereby it means that the range of input signal frequencies over which the device may operate without being distorted, or that is without being interchanged in terms of if information, giving false information from what you are supposed to be having. Then we talk about a perfect balance, the common mode gain. So I just want you to go through each and every part so that you understand your operational amplifier. Then also the operating of an operational amplifier, but what I want us to be talking about here is the circuit symbol of an operational amplifier having the non-inverting, the inverting input at the negative and also the non-inverting input at the positive. Then we've got VCC, which is the voltage at the plus and the negative. Then we've got the output voltage. So as you can see at the input, in this case, we've got two inputs that we can consider, the inverting and the non-inverting. So it's just going to be given in form of this nature. We've got the inverting input entering here to the negative, the non-inverting at 0.3 that is going to the positive. All of these combined together, they are going to go out to the output, in this case at the 0.6. So this is the pin layout of a dual inline 8-pin op amp. So that is the application of these op amps. So I just want you to go through and revise your theory part so that you understand each and every part of your op amp, because they might ask this theory part. So here we've got two considerations that we can have our op amp in terms of the diagrams. And as well, I want you to go through, guys, and see what is happening. So let us check each and every op amp that we are given in our syllabus, starting with the inverting amplifier. Remember, we saw from our diagram, if I am to take you back here so that you can understand, the inverting input is at the negative. Remember that, so do not confuse this part. All right, so if you are to check here, we are going to have that condition because we're talking about an inverting, which is the inverting amplifier. So the voltage at the input is going to be taken at the negative terminal, which is what the inverting input. All right, so we're going to have V in the input resistance. Then we also have RF at the output. So in this case, we're given the input voltage is given as V in, and the voltage output voltage as V out, and we've got the output voltage, which is this part at the output. In this case, between the voltage in and the voltage out in terms of their characteristic curve taken from 0 out of phase with V in is given. So this is the formula that you're going to have from our characteristic curve. We can also be asked to draw or to have this characteristic curve that we are given in this case. All right, so that is what we are going to have in this case. And I think with this information, we can be able to calculate the voltage at the output with this, which is simply here, we are talking about R minus RF over R in times V in, which is simply taken from the gain in this case. All right, so if we talk about RF over R in, this part of RF over R in, as we see, it's simply the voltage gain. So it's simply we are multiplying the voltage gain to the what? To the voltage that is in. So it's simply, whenever we're talking about output, we can simply show, in short, is the voltage gain times the voltage that is at the input in this case. So it's going to be minus voltage gain times the voltage in. It gives us the voltage at the output, depending with the type of amplifier, which is op amp that you are using, depending with the op amp that you are going to be using. So if you're dealing with an inverting one, you are going to have RF over R in. So it's going to be minus RF over R in. So this is what you're given here, and we are given the voltage gain of the amplifier is a set of values of the resistors R in and RF for the feedback in this case, all right, which is the ones that you are given here. That is voltage gain, which is V out over V in, or RF over R in, which is the one that I was explaining before. So that is it, guys. So we are given a question here to consider. The question is, we are asked, okay, the other thing is, in terms of our voltages, guys, we can have this negative is just for formula purposes, and negative gain over this. From the gain that we are talking about, we can just calculate our gain as it is direct, which gives us a positive, then the voltage as it is, which gives us a positive. The negative is just for the terminal that you are having, and this issue of like which formula are you using, but that condition is not going to affect us at the end. All right. So that is for a negative input voltage, the output will be positive and vice versa. This is another thing that you are supposed to consider if you are working with gain, because when you are dealing with the gain, you cannot know to say it's positive or negative. You're just calculating. But what is important is that if we are having the negative input, then our gain output will be positive. All right. Meaning to say we are talking about which input is it because of our what? Because of the type of op amp that you are dealing with, of which this part as well at the end does not even affect us. All right. But you're supposed to consider that for a negative input, we must have the output to be what? To be positive. So if we are to consider here, we are dealing with an inverting whereby the input is at the negative, our output must be positive on that condition. That is what you can also consider. So that's why you see here on this calculation, they are asking you to calculate the voltage gain of an inverting. So the inverting concept means our voltage at the input is a negative. The voltage at the input is a negative in this case. So if we have got a negative at the input, it means at the output, we shall have what? We shall have a positive, all right? Negative, positive, just like that. So in order for you to calculate, because the question here was calculate V out, like I said, V out is simply given from the formula minus RF over R in times V in this case, all right? So you can just substitute, or you can calculate the voltage gain aside, whereby we said our voltage gain is RF over what? Over R in, which is fine. But you can just use your formula direct to say our V out is going to be minus RF, which is RF, yes, 10 kilo ohms. So that's 10 times negative 10 times 10 to the exponent of 3 over R in, which is 1 kilo ohm. That's 1 times 10 to the exponent of 3 times V in. Because we are dealing with an inverting, the voltage V in is 0.5. Yes, we know that, but we take this as a negative 0.5 because we are referring to the voltage of a what? Of any inverting. The inverting terminal is connected to the what? Is connected to the negative terminal. So it is going to give us a positive at the end. So this one, we can just multiply direct on our calculator. That will be a positive 5 volts at the end, right? Negative, negative is going to cancel. So that is the idea of our questions. If you're answering these typical questions, then here we are given this part, we have got the non-inverting. The output voltage is in phase in this case with the input voltage and is given by, so we've got the formula, which is again the voltage gain times the voltage in, always voltage gain times voltage in. So in this case, the input, this is our V in, which is at the positive terminal in this case, right? Then we've got our RF and our R in, which is R1 at the input. So everything is there, and we've got our output in this case. So that is the best formula that we are going to have at the end. So if you have to calculate here, in actual sense, in terms of, like I said, in terms of our calculations, the negative that we are going to be seeing, it does not affect to say, yes, our answer is supposed to be positive, which we know because it's supposed to be negative because we're talking about inverting being positive, and at the end, when amplified, it's going to be a negative, all right? But if we are to take in terms of our normal gain, if we are to take this in terms of our normal gain, which is R1 plus RF over this, we're just going to use the positive as it is, right? So do not confuse on this part. Because most of us, we confuse, am I going to use a negative? Am I going to use a positive? So here we can just take our formula direct. But on the inverting part, because we have a negative on our formula, we shall take V in connected to the negative terminal. So it will be negative, negative. All right. So do not confuse on this part. So that's here. Yes, we can calculate the gain like this part, what they did, or you can just combine at once. Since we want to calculate the voltage, All right, also here it was not, because they wanted the voltage gain and the V out at the end. So that is where we are limited in this case, because they wanted us to have the gain first. But if you wanted to calculate the voltage at the output, you're simply gonna use your gain at once, R1 plus RF over R1 times the voltage at the input in this case, which is V in. So you can actually use that, which is this part representing your voltage gain. All right, so I want you to try and use that part and see if you are gonna have the same thing or the same answer. Then we move on to the summing amplifier. This is the one that has got the voltage is taken to the negative, but we are given a different voltage is entering our input. This is the input. Then we've got the feedback to the what? To the output. So a summing that is adding, we are talking about voltages connected together, adding up together. So in this case, when connected to the negative, we are going to have our gain as minus. We are going to have minus RF into our voltage output. All right. So now what is going to happen is that, as we can see here, at the output, we are going to consider to say there's voltage and resistance. So we're going to have the current there, the voltage and resistance current, voltage and resistance current. So in actual sense, we are supposed to have the voltage at the output as the current. It is supposed to be given as current times what? Current times the resistance. But the resistance that we are is RF. The current that we are considering now is the total current, which is taken from V1 over R1, V2 over R2, V3 over R3. That is how we are going to have this. And it's going to give us a positive at the end. But because of the formula that you are using, we are going to take it as a negative at the end, all right? Because it's minus RF. So these formulas we are given as they are and use them as they are, right? So here we are simply saying, if all resistors are equal, if these resistors are equal, it means this current will be the same, this current, and all are equal in value. So if these resistors are equal in value, therefore our voltage now at the output is simply going to be, because we're having same resistors throughout. So meaning to say the current here is going to be the same. So we're going to have V1, V2, V3 times, which is here supposed to be minus R is equal to, just like this, is equal to, all right? So you're just going to consider V1, V2, and V3. That's an equal, not minus. There's an equal to. All right, so here we are given, that's an example. I think this one, just cross-check your values, but here everything is fine. R1, R2, R3. So from our formula, V out is minus RF over V1 over, we have the formula for a summing amplifier, op amp in this case. So I think everything is direct and your answer. Then we've got the integrator, which is the one that has got a capacitor on the feedback. So we are going to have the capacitor. So in this case, we have got the rate of change at which the output voltage changes is related to the value of the input voltage and that of the instant, and is given by because there is a change in capacitance value. So we are going to see at the end that the rate of change of the voltage is going to be V in over CR in volts per second, whereby we're going to consider the voltage at the input, the capacitor value times the resistance at the input, which is our R in this case. All right, so that is going to give us V out. So that's the idea in this case. So meaning to say, V out is 90 degrees out of phase with the input, and the output voltage is given by. So in short, we can have our formula as V out is minus 1 over RC, the change, the integral of V in, which is the change. Simply, you're going to consider the change in V in, which is V in over CR in. Okay, so that is the formula that we can have at the end. And I think that's what you're given here. The rate of change from voltage over, we can have here the rate of change of the voltage out. We have got this in volt per second. So that's the idea there. So you're just going to substitute, since we need to calculate the rate of change there. All right, so I think this is direct, guys. Then a differentiator now. Do not confuse to say there's a capacitor. Now we have got the capacitor at the input, but the feedback is giving us what? A resistor at the end. That's a differentiator. It's different from what? An integrator. An integrator, the input is the resistor. Then at the output, which is at the feedback, we've got a capacitor in this case. Take note between these two, because they might ask you to draw these diagrams. That's why I just want you to see the diagrams and the formula so that we work them together. And also the formula for the voltage out, which is minus RCD dt of what V in, which is the derivative of V in this case. Do not worry, we are not going to differentiate anything. All right, do not worry about that derivative that you see there. Then the last part is a comparator, whereby we are given V1 and V2, VCC minus VC and V out. So there they can ask you to draw the comparator and also the waveform of a comparator. So that's it. An op-amp is low, what, okay, indicate true or false. All right, so these are some of the questions that you might be given on op-amps. So as you can see, it's a direct thing that you just need to know your formulas and how to apply the formulas that you're given. All right, so this is question paper of April 2020, whereby we are given calculate the voltage output and gain of a non-inverting. All right, so this is a non-inverting amplifier. If V in is 5 volts, R1 is 25 kilo, and RF is 30 ohms in this case. All right, okay, so remember, we talked about this. I'm not gonna redraw this part. Maybe I can just show you back so that we do not waste much time on redrawing these diagrams here. I think it was here. Let me check on this one. I think it must be here. All right, this is the inverting. All right, we need, all right, where is it? I think, all right, here on top, the non-inverting. Remember your diagram, guys, and also your formula. Like I said, I'm not gonna redraw this because we talked about this. So just gonna refer to each diagram that we talked about. All right, so we saw that in this case, the gain, because we need the output and the gain. So instead, we can just start by the gain. All right, from what you're given, we've got R1, RF, and V in. Remember, for the non-inverting, our gain, which is our voltage gain, is given by R1 plus RF over R1. Okay, that is, we are going to add these two, which is R1, that is 25 kilo ohms. All right, so here we've got 25 kilo ohms. This is supposed to be in the same units, guys. We are supposed to have these values in the same units. Actually, we are supposed to have these kilo ohms also. So it's just a typing mistake, or maybe when I was editing this part, I just removed by mistake this one. So it's a kilo ohms there, not 30 ohms. It's too much from 25 kilo ohm. All right. So these are kilo ohms, all of them. So we are going to have 25 plus 30 over R1, which is 25. So that is going to give us the voltage gain in this case. All right, our voltage gain is going to be given as 2,2. So that's 2,2. All right, then if we could have, maybe we calculated the voltage, maybe we calculated the voltage and we have the output voltage. Our gain was going to be V out over V in. But that will be a condition now when you calculated this voltage direct. So let's see and prove this. Remember, we want the voltage also. So maybe you started by calculating the voltage direct, which is V out. Remember, V out for a non-inverting is given as R1. This is non-inverting, which is given as R1 plus RF over R1, which is our gain times V in. So that is, we're supposed to obtain R1, RF, which is this part that we substituted 25 plus 30, because these are all in kilo ohms. So there's no need for us to write 25,000, 30,000. Yes, you can do that, but they are all in kilo ohms, all right? Divided by 25 in this case times V in, our input voltage, which is 5 volts. So that is going to give us V out of 11 volts if we simplify properly. Then in order for us to have the gain there, we're just going to substitute, which is 11 V out over V in, which is 5. So you're going to obtain the same answer of what? Of 2,2. That is on a condition that you started by calculating what? the output voltage. All right, then we are given a summing amplifier, op amp in this case. Remember, a summing is the one that is taken with resistors going into the op amp, in this case with V1, V2, and so on, connected to a negative, then and so on and so on. I think we saw that from our diagram. I'm not going to talk about this. So we've got R1, R2, R3, V1, V2, V3, and our RF. So that is the condition of our operational amplifier, which is a summing amplifier. So the question here, as you can see, we've got R1, R2, R3, and we also have RF, V1, V2, and also we've got V3. So the question was to calculate the output voltage. Remember, for a summing amplifier, we saw that the voltage at the output is given by minus RF into these values. They are different. So we're going to consider V1 over R1 plus, we also have V2 and R2. So we've got V2 over R2 up to V3. So we also have V3. So it depends with the number of resistor voltage that you are given. Maybe there are 4 or 5, you just have to consider, but we are given 3 there. So we are given minus RF, which is minus RF being, these are kilo ohms, but on this part, I have to consider this kilo ohm because it's not part of these ones that are down here, unless you are to factor out the kilo, then you just write the numbers as they are, which is fine. All right, so you can do that to just write this as minus RF because all these values are in kilo ohms. So our RF here, which is 22, so it's going to be minus 22 into V in, our input, it's 5,5 over R1 here, R1, which is 10 kilo ohms. So it's just going to be 10 because here we wrote this as 22. We have already factored out the kilo to cancel with this one on the negative 22. All right, plus V2, which is V2 here is 2,5 over R2 in this case. All right, so this is R2, which is our R2 is 12. All right, plus V3, which is the voltage 3. It's this is V1. All right, V2 and, all right, that's V2, V3, and R3. All right, so I think we are together. R3 being 17,5. So that's 17,5. So like I said, you can use the kilo ohm as times 10 to the exponent of 3 if you want, but you can just ignore that because we have kilo ohms also at the end. So that was going to give us a negative 17,94047, something like that, which is going to be 94047. So that will be a 0 there. So we're just gonna leave it like that. So that's it. I think this is just direct. Then 6.3, we are given to calculate, in this case, the input. Now we need input. So that's V in of, if the integrating amplifier is the rate of change, take note we are talking about an integrating amplifier in this case. All right, just a sketch. Remember, our integrating amplifier is the one that has got an input of a resistor and an output, which is the feedback of a capacitor in this case. All right. All right, just do not forget your diagrams. All right, so this is negative, positive, like this. So we're gonna have something of this nature. Remember, that's it. We've got our V in, this is R in, this is our capacitor, and this is our V out. So we are asked here to calculate V in, given that it has a rate of change of 0.9 volts per second. So we've got the rate of change. Remember, we have got the formula for the rate of change. So the rate of change here is 0.9 volt per second. And we are given the capacitor value and R in. How do you calculate the rate of change? That is the question, which is from our V out, our rate of change. In order for us to have V out from the rate of change, because this rate of change is from the output. All right, let's just write as V out. So you can simply say our V out is equivalent. Remember, our formula was V in over RC, okay, which is measured in volts per second, which is the rate of change. So we have this rate of change and we want to calculate the voltage in, which is this one. So in order for us to have this V in, we are just going to cross multiply this to the rate of change, and we've got our V in. So our V in is going to be V out, which is the rate of change, times RC, which is R in and the capacitor there. So I think we can make this the subject, and you can substitute everything according to what you understand. If you understand the idea of substituting here direct, is fine. You can do that. But if you understand this of making the subject, you can make it the subject, which is fine. So we need V in, and we've got V out, which is the rate of change of 0.9. So that is going to be 0.9 multiplied to the resistance, that is the input resistance of 25 kilo ohms. So this is 25 kilo ohms times the capacitor value, of which we are given our capacitor value is 100 microfarads, which is microfarads, that is times 10 to the exponent of -6. So that is going to give us the input voltage, which was 2.25 by calculation. It got something like 2.25. So that was it. That is how they can ask these questions. You just have to be careful the type of diagram that you're working with, the formula for that op-amp. You are supposed to know each and every op-amp in your syllabus, and the formulas of each and every op-amp in your syllabus. So the first part, that was it. Then we've got another question, which is Feb 2022 exams. 6.1, it was a non-inverting amplifier. Take note, a non-inverting. We talked about this before on our first question. Now they want us to calculate the output voltage in this case. Remember, we talked about this non-inverting on our April 2020, the last question that we just talked about here. So let's just save it. You still remember here. The first question was a non-inverting. So this one is not going to change. Our formula still the same. Yet they do not want us to calculate the gain, this, and they want us to calculate the voltage output. Yes, you can calculate the gain aside, which is fine, but you can just go straight to the formula. Remember, for a non-inverting amplifier, the voltage out is equal to the voltage gain, which is R1 plus RF over R1 multiplied by the voltage at the input. So that's what I'm saying. You can calculate this aside, which is your voltage gain aside, which is fine. Or you can just substitute R1, which is you are given 1 kilo ohm. These are in kilo ohms both. So you're just going to substitute. This is kilo ohms is just going to be 1 plus 7 over R in, which is R1 times the voltage at the input, which is V in 2.5 volts. So you're going to multiply to 2.5 volts. So that is going to give us V out at the end, which is going to be 8 times 2.5, which is 20 volts. So that will be 20 volts in this case. All right. So that was it. Then 6.2, you're given draw neat labeled circuit diagrams of each of the following operational amplifier. Now you see the type of question that I was saying, that they can actually do that, to ask you to have a diagram of each of these. All right. So the first one that we are given, it's a non-inverter, and is the one that we talked about here, because this one, it was a non-inverter. So you're supposed to know this diagram because it's the one that you calculated before. But anyways, just for revision purpose, let us just see here. Remember, our non-inverter, it looks like this. Let me just show you to this piece here so that you can see it here. So remember, our non-inverter is going to be given this way, whereby we've got V in R1 and RF. That is the most important part here of our RF. Where are we having our RF in this case? Then we've got our V out in this case. All right. Then we talked about the issue of gain, finding gain, which is R1 plus RF over R1, then calculating the voltage at the output, which is that gain times the output. All right, so I think this part just directly talked about these diagrams. Then now an integrator. On the other part, we've got an integrator. From this part, we have got an integrator here. Remember your integrator, the input is a resistor. Like I said, you're gonna have the input as a resistor, then the output, which is a capacitor. So you have to take note, this is your R in, then this is the capacitor at the feedback, V in and V out. All right, so I think that's it. Then we've got the last part, which is an inverter in this case, which is an inverting one. That, remember, we talked about non-inverting. Then we've got the inverting, which is connected at the negative terminal this time. So we've got R in connected to the negative terminal, and we've got RF, V out, V in. So that was the condition. 3 marks, 3 marks, each and every question that you're given there. So as you can see, if you know your diagrams, you have higher chances of scoring a lot of marks from your question. As you can see, 9 marks out of 4 is from the drawing part. So know your diagrams, As you can see, this one, it was just on the diagram part. And you see the other part here again, to draw a neat symbol or label of an operational amplifier. I think we talked about this on the introduction part of our operational amplifier. So you're supposed to know each and every sketch of what you are given, guys. You're supposed to know the sketch of each. All right, so let us just try to have our sketch here. All right, this is from the question paper of August 2022. Yeah, before I talk about this thing, this is August, and I just hope, let me just show you, because I have this sketch somewhere. So I'm just gonna show you here. All right, so this is the one. Let me just show you on this side, because it's gonna take us time. All right, so this is the one that you're gonna consider. All right, remember our input and output, we talked about this, guys. So that's what you need on your part, and everything is clear there. 3 marks to have that sketch. And we talked about this. And so 6.2, you give a name and give the purpose of each of the following of the 2 input terminals of the amplifier. Remember, at the input, there is an inverting, non-inverting in this case, inverting being negative, non-inverting being positive. So now they need, what is the purpose or the use of those terminals? All right, so an inverting terminal being a negative, that is the terminal that produces an output in antiphase with the input. So it produces an output with antiphase. All right, that is the one that we're talking about, to say if the input V in is a negative, then V out is going to be considered as a positive. In this case, in antiphase, we're just going to have a positive value. But for a non-inverting, which is a positive, which has got connected to the positive, the terminal produces an output in phase with the input. That's why we see that whenever we are talking about a non-inverting terminal, our answers, they're all positive, because it is connected positive and it's in phase. So we're going to have output which is positive also. All right, so that is the condition. I think here we explained on this part here. Let me just take back and see. All right, so we talked about this in this part. All right, the non-inverting, the output is in phase with the input. So if we've got a positive here, our output is going to be a positive. But if you check for the non-inverting, our formula is having what? A negative, because our output must be a reverse, which is a negative. So you're going to have negative of the gain. That is the condition there. I think we are together. We are together on this part. So let us check the other part. I think it was just a calculation there. All right, no, this is the one. All right, the other part here, it's a calculation. So we talked about these 4 marks for that. Then we are given 6.3. That is the feedback resistor of an inverter is 1.5 kilo ohm, and the value of the input resistor is 1 kilo ohm. Determine the output if the input voltage is 50 millivolts in this case. All right, so what are we talking about in this case? We're talking about an that is an inverting, which is the one that gives us what is opposite to the input in this case. All right, what is opposite to the input, because we are saying it is connected to the negative. So the output must be a positive. All right, but on our formula, what is the formula? The question is determine the output voltage. Remember, the formula is given as V out is given as minus RF in this case over R in, but it opposes now the output. So meaning to say the input there that you're going to use is a negative. All right, so you're gonna have our V out as minus RF. We have RF, the feedback resistor RF 1,5 kilo ohms. So it's 1,5 over R in also in kilo ohms. So that's 1 times the input, which is at negative 50 millivolts, which is negative 10 times negative 50 times 10 to the exponent of negative 3. So our V out will be a positive in this case, which is going to be something like 75 times 10 to the exponent of negative 3, which is actually negative 75, because this, you can just multiply these two here because we have got times 10 to the exponent of negative 3, which is milli. So you're going to have positive 75 millivolts in this case, okay? Or if you want, you can just ignore the negative of the voltage here. You use this as a positive, but you must know that at the end, that our answer is supposed to be a positive because it is opposing what we have at the input, all right? At the input, negative, at the output, positive. But for a non-inverting, it's in phase. The output and input, they are in phase. So output positive, input positive, output positive. That's they are in phase. But this one, there is going to be a reverse. So I think that's what we had in this case, which was 10 marks for everything, which is from August 2022 exams. So this was actually August 2022 exams. Let me check here. Supposed to at least have another question, but I think these are all of the typical questions that you might be given. All you just need is to work on your revisions in this case to know each and every part of what you are given. It's very, very important to know the circuit diagram and the calculations for what you are given, the circuit diagram, and also the calculations that follows to the diagram that you are dealing with. If you can do that, you'll be able to answer any question, and also to know the advantages. Yes, we do not have a question that we answered on the advantages, but as I illustrated on the beginning of the class, that we also have the advantages that can be considered, and also the characteristics, everything that you are given on your theory. Try to read up and understand what you are given from your advantages of the op-amps, going to the characteristics of an ideal op-amp and a real op-amp, to the calculations and to the diagram of each and every operational amplifier, and also understanding the gain concept and calculating of the voltage output from the gain or direct from the formula, because it's one and the same thing that you are given from there.